So if we deal with sum of square changes in z, in the limit, when the intervals get increasingly small, we get a value t. The interesting thing is that if we take away the square, instead of looking at the sum of square changes in Brownian motion, we look at the sum of absolute value of changes. So this can also be written as a sum of the absolute value of those yi's. Yi's being the normal random variables, and of course times delta t. So let me write it up here where I have a little more room. This can be written as the summation of y I h times the interval length is h. Right, so here I'm using the formula that the change in z is approximately a normal random variable y times the interval length, which is h. If I only now, instead of squaring the y's, which we did for quadratic variation, for total variation we don't square, we just use absolute values because we don't want cancellation. It's, first of all, easy to see that v, the total variation, is in fact bigger than the quadratic variation. And the reason is, when we square small things, we make them smaller. And we know that the change in z, as h gets smaller, the change in z will get smaller, and one finds in general the square of it is going to be smaller than the absolute value. So certainly we expect that v2 is going to be smaller than v. The remarkable thing is that if we remove the square and just use absolute values, it actually becomes infinite. If we define this total variation in Brownian motion by the absolute change over intervals of time, the sum of those absolute distances goes to infinity as the number of intervals grows. And this can be seen easily if we use the approximation where y is binomial, plus or minus 1, because then the summation of y times square root of h, and oh, I'm now realizing that I made a mistake on the prior slide. In this summation, this should have been a square root of h, right? Because the change in z is a normal random variable times square root of the delta interval. It's the variance that's h. The standard deviation is square root of h. So if we go back, we see if we approximate y with binomials of plus or minus 1, then in fact we get a summation of n times square root of h. Well, what's n times square root of h? H is equal to t over n. So if I take n times square root of h, I get this value, square root of tn. And what happens as n gets big, that just blows up. It's quite a remarkable, it's called the infinite variation property, that if you take any Brownian path and you break up the total interval into subintervals and you measure the absolute change in the z's from the beginning to the end of that subinterval, and you add up those absolute changes, as you make the number of subintervals grow, the total length of a Brownian motion becomes infinite. It's almost as if one could take a segment of Brownian motion on the interval from 0 to 1, it's almost as if it literally has infinite length, that if you could, as a string, grab the time 0 value and the time 1 value, it would be a string of infinite length, that it has so many zigs and zags and so much variability that the total length of every Brownian motion is infinite. It's quite a remarkable property. The other property of Brownian motion has to do with infinite crossing, which is a very deep result, which you are not expected to know the details of. I'll just explain to you what the result is. It turns out it follows from some interesting properties of Brownian motion that are not explored in this book. What infinite crossing says is that if I take any interval 0t, every Brownian motion is going to cross the x-axis an infinite number of times. In other words, it'll never happen. The probability of getting a path that looks like this, where it stays above, is effectively 0. That every Brownian motion starting at 0 is going to cross the x-axis an infinite number of times on every interval, no matter how small. We can make the interval as small as we want, and that Brownian motion, again, going back to my intuitive, it zigs and zags so fast and so frequently that over any interval of time, it's going to cross the x-axis an infinite number of times. And this is a very deep result relating to symmetry and reflection properties of Brownian motion. But again, it's quite a startling result, and again, one that challenges, is it possible that such an exotic process can indeed exist? And the answer is it can.